Okay, you might wonder here, from the previous video, this a of x, 1x, let's say x squared dx, as I said in the previous video, could be also bx, another antiderivative of x squared plus a constant. And I said that c could be any constant. But here, there, I derived that c equals to minus b1. So what is it? It is not every constant, every numbers. C is just one number here. So the point is that, for a another antiderivatives, differ by a as the number c. One differ as c equal to 1, one may differs as c equals to 3. So this one differs as this. Not all the antiderivatives should differ as any number. I said once you found some antiderivative of this, I said let's consider this, which derivative is 3x squared over 3 or x squared. So this is our b of x. So for this b of x, we got 1c. And this is also an antiderivative of x squared, which derivative is x squared. So, but here c is not equal to this one. Anyway, let's have some other examples. Okay. How about this scenario? 0 to 1, 5, x to the power of 6, b of x. An antiderivative of it is, this is an antiderivative of it is x to the power of 5. So that would be from 0 to 1, which is 1 to the power of 5 minus 0 to the power of 5, which is 1. And in order to prove the theorem which says that the derivative of this equals to f of x, we do something like that. You know, 1, this is x. Okay, we deal with derivative, so we should first calculate this difference. Let's call it delta x. Okay, minus a of x over delta x, and the limit of this as delta x goes to 0 is the derivative of a of x. Okay, now what is this? A of x plus delta x. X plus delta x is this point. So this means that here, okay, is the area, this area. Yeah. And the a of x was this area here. So the difference would be this area. So, you know, I'm not gonna write the whole proof. You could find that even at Wikipedia. So this is something like that. We said as delta x becomes smaller, this area becomes smaller, and you know, finally that would be equal to the f of x. You know, as I mentioned before, you know, the natural scientists and engineers, also maybe economics, don't do the Riemann-Sum stuff. Don't work with that. Because, you know, calculus and integral calculus and derivatives were found about 200 years before Riemann himself. But they used it in every branches of science. It was they needed, and they were happy. Nothing wrong happened there. So, you know, instead of this, which we call the rigorous version of the integral calculus, or calculus generally. And instead of that, they use the infinitesimals. Let me write it here. Infinitesimals. Which, let me talk about it here. Let's first prove the theorem here using the infinitesimals. This is our function, say. This is 1. This is x. And you know, instead of delta x, here we use the infinitesimal version of it, which is dx, we call, which means which length, this length, is infinitely small. That's it. Doesn't have any assigned values, but we call that infinitely small. Okay, now ax plus dx minus ax over dx, this is the derivative of a of x, and there is no limit or anything. You might be familiar with that from the derivative courses or lessons. I mean the differential calculus courses or lessons. Okay. Now this is the area of from 1 to here. This is the area from 1 to here, and the difference is this area. And since it is an infinitesimal, which means infinitely small, so this would be a straight line instead of being curved. So this thing would be like that. And you know, this might sound wrong, but you know, this ends up with the same result as doing the Riemann limit stuff, the limit of the Riemann sum stuff. And scientists work with that for centuries and still working with that, but not the mathematicians. Let's say not all the mathematicians. I know a group of them which don't like these things, but I'm not sure about the rest of them. Okay, let's talk about more in the next video.